So hello and welcome to Diggin In. I'm Lindsay Randall, the host of the speaker series. Diggin In is a series of live presentations with archaeologists from around the country, co-sponsored by the Robert S. Peabody Institute of Archaeology and the Massachusetts Archaeological Society. Join us every other Wednesday at 1:30 p.m. Eastern Standard Time through November for our presentations. For a schedule of dates and presenters, please visit us at peabody.andover.edu or at the Massachusetts Archaeological Society's Facebook page. Viewers are able to submit questions directly to me via the chat function on the side of your Zoom screen. At the conclusion of the presentation, we will give our speaker time to answer as many questions as they can, with the understanding that they might not get to all of them. And today we are excited to have Miss Grace Bello. She is a recent graduate of the University of Massachusetts, Boston, with her master's in historical archaeology. Miss Bello has been an archaeologist working in CRM, universities, museums, and for the National Park Service since 2013. And currently, Miss Bello is an archaeological technician for the Northeast Archaeological Resources Program of Region 1 of the National Park Service. She is also a trustee of the Massachusetts Archaeological Society. So welcome, Miss Bello, and thank you for joining us today.
Yeah, thank you guys so much for having me. Thank you to Lindsay, the Andover Peabody and the MAS for setting all of this up and for having me come and speak. So let me share my screen. All right. There we go. So hopefully everyone can see my screen. How do I put this away? All right, very good. All right. So this presentation will cover the research method and conclusions for my master's thesis, which developed a technical X-ray fluorescence or XRF method to determine if elemental variations in flat glass artifacts can be used to identify and date those artifacts and associated archaeological deposits. The elemental variations of strontium and lead the elemental variations of strontium and lead in flat glass are specifically important to this research, as these two elements can be directly associated with manufacturing changes that occurred in the English glass industry during the 17th century. Due to the evolution of raw materials used in this industry, there is a detectable change in the elemental composition of manufactured glass products, which is measurable using XRF analysis. To build this method, flat glass fragments were tested from 3 archaeological sites in Plymouth Colony, one of the first English settlements in New England. First permanent English settlements in New England, I'm sorry. The map on the right here shows the locations of the 3 sites that produced glass that were tested for this research. The site farthest to the south on this map is Burial Hill. This site is the location that has been subject to extensive excavation by the Andrew Fisk Memorial Center for Archaeological Research since 2013. As of the 2018 field season, 164 glass fragments were uncovered in mixed and sealed 17th century deposits that were included in this study. The Burial Hill site is an eastern portion of the initial nucleated Plymouth settlement. 7 years after the establishment of Plymouth Colony, the company that funded the original settlement was disbanded, and the settlers' shares in that company were divided into stock of cattle and plots of land that were farther away from this initial nucleated plot. Over the next few years, settlers moved out to these satellite plots of land, and these other 2 sites that were studied are 2 of those satellite properties. The northernmost site on this map is the Alden first home site. This site was occupied by the Alden family by 1632 till at least the end of the 17th century. The Alden site was excavated in 1960 by Roland Robbins, who maintained horizontal control during excavation, but vertical control only within the cellar at the western extent of the building. The Robbins excavation produced 764 glass fragments that were tested in this research. The remaining location on the map I had showed you is the Standish site, which was occupied by the Standish family by 1632 until around 1665 when the primary dwelling on the property burned down. This site had been explored at least twice before it was extensively excavated by Reverend Benjamin Kent in 1829 and then James Hall in 1856. Only 21 fragments of glass were able to be tested from these excavations, as much of the collections have been lost over time. With the addition of the fragments from the Standish site, a total of 949 fragments were tested during the course of my research. The glass fragments uncovered at these three sites can be dated because of a major manufacturing change that occurred in the English glass industry right around 1660. As manufacturing technology and access to raw materials evolved in England during this time, the raw materials used to produce glass also changed, which is reflected in the elemental composition of the final glass products. Research and analysis conducted by David Dungworth has shown that during around 1660, kelp began being used as a flux in which began being used as a flux in glass manufacturing. And a flux is an alkali product that is used to lower a melting temperature of an overall glass melt. This flux addition produces a comparatively high strontium composition in the produced glass product. Using this notably high strontium composition and a proposed date of introduction of the kelp ash flux, window glass can be dated to production after 1660. However, dating glass manufactured before 1660 is a little bit more complicated, as glass houses did not unanimously transfer all to this kelp flux all at once. Based on analysis of historic glass production and comparatively low strontium composition, flat glass can be dated to production between 1567 and 1700. This period of manufacturing change in the English glass industry also saw variations in the use of lead in different types of production. As determined by my thesis research, lead composition is useful in identifying window glass versus case bottle glass. Sometimes at archaeological sites, window glass can be so highly fragmented, it's really, really hard to identify, or rather, flat glass is so highly fragmented, it's really hard to identify. Therefore, it's really important to have a method to be able to differentiate between these two. On the right here, you see window glass fragments with lead cane staining. And then on the right, you actually have case bottle fragments. And if these fragments were any more fragmented than they are, it would be kind of hard to identify them. Case bottles, shown here in the bottom image, are commonly called gin bottles or Dutch gin bottles today and in historic documentation. These bottles were commonly used for shipping in case boxes, for carrying alcohol and various types of oil. And then the top image is a typical 17th century casement window. Throughout the data collection process of my research, it was discovered that relative high lead composition can be used to identify case bottles, and relatively low lead composition can be used to identify window glass fragments. However, this identification is only useful for glass products produced without that kelp flux, so before 1700. Both windows and case bottles were really common in 17th century English and colonial homes, so the ability to differentiate between the two of them is pretty important. For this dating and identification method, a Bruker Tracer 3 portable X-ray fluorescence spectrometer, or simply a pXRF, was used to determine the relative strontium and lead composition of the flat glass tested. An XRF shoots X-rays into an object which temporarily excites the electrons orbiting the atoms of that object. After X-rays come into contact with the atoms, photons are emitted from the electrons of each element in the object. As these electrons return to a stable lower energy state, the energy is released in unique measurable amounts that correspond to specific elements that are processed to produce an energy spectrum graph, which is the graph that is shown here. Each of the peaks shown in this graph represent an element that is present in the artifact, and the height of each peak corresponds to the amount of that element in the artifact. The method built during this research used net peak area, or NPA, to analyze the raw spectra and results produced by the XRF. NPA produces a semi-quantitative analysis based on relative abundances of elements compared. This enables a comparison of elemental compositions of objects without a true calibration of the data. All right, this is the fun part. Shown in these two charts is the strontium composition of all 949 glass fragments tested. These two charts are shown here to show the frequency distribution of strontium counts and to compare the distribution across the 3 sites. So here you see in blue the glass fragments from the Alden site, in red from Burial Hill, and then in green from Standish site. There's a clear high frequency of strontium counts around 22,000, which you can see here and also here. Based on this high frequency of counts, a separation was drawn between relative low and relative high strontium counts right around 29,000 counts, which is somewhere right around here. The high frequency of low strontium counts likely represents relatively standardized raw materials that were used in English glass manufacturing that did not include the kelp flux. During the early to mid 17th century, a restrictive glass monopoly existed in England that likely contributed to high standardization in this industry. The high frequency also suggests that low strontium glass might have been more likely easier to access throughout the 17th century. This can be explained by the fact that this type of glass was produced over a wider period as compared to glass with high strontium composition, which is only produced after 1660. Comparatively to this tight range of low strontium glass seen here, all 3 sites display a much wider range of high strontium count, which you can see here. A wider range of high strontium compositions suggests that there was a period of experimentation in English glass production in the late 17th century after the switch to kelp ash, causing a wider variety of glass composition. There's also significant differences in high strontium ranges between the 3 sites. Glass from the Alden and Standish site, seen here, have much tighter ranges of high strontium composition as compared to the Burial Hill site, which has a much wider composition. This suggests that glass samples likely vary in either date of production or production location. So these next 2 charts show the lead composition of all the flat glass that were tested from the 3 sites. Both charts are displayed here to show the bimodal distribution of the lead composition and also to compare this distribution across the 3 sites. So again, here we have in blue from the Alden site, in red from the Burial Hill site, and green from the Standish site. These charts display 2 clear groupings of lead composition that are separated a little bit over 4,000 counts, which you can see right here and right here. These 2 groups account for lower lead composition in window glass and higher lead composition in case bottles. This conclusion is most clearly shown in the lead distribution of glass fragments excavated at the Alden site. Seen here in purple are the positively identified case bottles, and in yellow you see the positively identified window glass fragments. And these visually identified case bottles and window glasses are separated right around that 4,000 count that we saw in the previous chart. Once these lead groupings were discovered, visually identifiable case bottles and window glass fragments were used to classify the elemental and physical characteristics of each type, so previously unidentifiable highly fragmented shards could be classified. This box and whisker plot displays the lead and thickness of all the visually identifiable window glass and case bottle fragments. So that means anything that we could identify as case bottle is here based on its physical attributes, and then anything identifiable based on its physical attributes for window glass is shown here. This plot shows a clear distinction between these two groups. So a quantifiable number to separate out these two artifact classes based on their lead composition was calculated using the mean and standard deviation of each group, which is this number down here. The validity of separating glass fragments into artifact classes based on their lead composition was tested using an independent sample t-test. This test was also applied to using thickness as an identifying characteristic for case bottles versus window glass. This test was used to determine if the averages of the visually identified case bottles and window glass fragments were statistically different based on their lead composition and thickness values. This test concluded that the visually identified artifact class population averages were statistically different from one another based on their lead composition and their thickness, which suggests that case bottles and window glass fragments can be identified using these two attributes. During the course of data collection, an important characterization about case bottles was discovered. So shown in this scatter plot are the strontium and lead composition of the visually identified case bottles from all three sites. Again, in blue, we have our Alden site, and then in red, we have the Burial Hill, and green, we have Standish site. There is a clear separation between the low strontium case bottle glass and high strontium case bottle glass, which was produced after 1660. According to Eleanor Godfrey in The Development of English Glassmaking, case bottles were often made in window glass houses. Therefore, the switch to strontium is also a characteristic that can be used to date case bottles. But with this switch to kelp, the lead distinction for identifying the two different artifact classes is no longer useful, as you can see here. The first important conclusion of this data is that the high strontium fragment, unless otherwise visually identified based on superficial characteristics, cannot be identified as either window glass or case bottle glass. This methodology is only useful for identifying low strontium glass. Based on the information and calculations I just discussed, all 949 flat glass fragments tested from the three sites were assigned production ranges, which is shown in this chart. So on the right, we have our characteristics for low strontium glass and if they were identified as case bottle or window glass and their identifying characteristics. And then based on the three sites, these are the numbers for each of those sites identified into the two separate groups. And then on the left, we have our high strontium glass based on the three sites and the characteristics that were used to identify those. The scatter plot I showed you before also reveals a second important conclusion about this data, which can be seen in the compositional differences between case bottles from Burial Hill and from the Alden site. So in red, we have our Burial Hill case bottles, and in blue, we have our case bottles from the Alden site. The case bottles from Burial Hill tend toward high strontium and low lead composition, while the case bottles from the Alden site tend toward high lead and low strontium. This difference is likely a result of the two sites being supplied with case bottles produced at different locations, although a difference in the time of production is also definitely a possibility. Both sites were occupied throughout the 17th century. But case bottles and other flat glass commodities that were produced after 1660 are seen in much greater abundance at Burial Hill as compared to the Alden site, which had very few of these products. This is possibly due to the Alden family living farther away from the market center in Plymouth, and that this single family were the only procurers of glass products to the site, while the Burial Hill site likely had more occupants and were physically closer to the market. This interpretation is strengthened by the differences in high strontium ranges between the two sites. A wider range of high strontium glass at Burial Hill supports the argument that occupants at Burial Hill had access to a wider variety of goods being produced at a wider variety of production locations. Based on the XRF analysis and interpretations of the lead and strontium distributions between the three sites, the dated fragments were able to help interpret artifacts that were previously less interpretable due to the age and type of excavation at two of the sites that I studied, being the Alden and the Standish sites. almost half of the glass produced after 1660 at the Alden site were found in the bottom two layers of the cellar that was at that site, while the other half of those high strontium fragments were found along a northern foundation wall. This suggests that the high strontium glass products were utilized by the occupants of the Alden site before the structure was abandoned and not deposited at the site after the structure became a ruin in the early 18th century. Based on this conclusion, the occupants of the Alden site, while consuming less of a variety of newer products, were still participating in an English consumer market in the late 17th century. For the Alden site, there are only 21 flat glass fragments tested, but with the knowledge that the dwelling burned down in 1665, the presence of high strontium glass produced after 1660 supports our understanding that the site was probably used as a dumping ground after its destruction. This analysis was also useful at the Burial Hill site, which has very precise vertical and horizontal control from excavation, and therefore we were able to use these dated artifacts to assign TPQ dates to archaeological deposits that produced the glass that I tested. The identification method was also able to be applied to 92% of the total fragments tested for this thesis, with an accuracy of about 86%. Before this XRF testing was conducted, 732 flat glass fragments of the total 949 were identified as either just flat glass or they were misidentified as window glass. So using this method, we were able to assign proper classification to these artifacts, and more extensive analysis could be done on these collections moving forward. This method was also able to help interpret distinct differences between visually identified case bottles from the Burial Hill and Alden sites, which speaks to difference in access to procurement between those two sites based on the different ranges of their high strontium products. And finally, this analysis supports the idea of a glass industry experiencing a period of experimentation in the late 17th century, with the wider range of high strontium composition being compared to the much tighter range of low strontium composition. By comparing these different ranges, this data could suggest that after 1660, glassmakers were able to experiment with new manufacturing styles in a period of release following a fairly restrictive monopoly. The use of this methodology at additional 17th century English colonial sites could establish a much more thorough understanding of English glass composition and create a more detailed chronology of black glass throughout the English colonies. Thank you guys so much for coming. That was my talk. If you have any questions, you can shoot them over into the chat, and I'll try to get to all of them.
Yes, please do. Send them in via the chat function. You can see the little thing down at the bottom. Can I start with a question though as the host, Grace?
Yeah.
What got you to pick glass to research?
Yeah, that's actually a super good question. So initially when I started my graduate degree at UMass, I was talking to Krista Baranek, was my advisor. She's the light of my life, and she suggested me working on the Alden collection, and they have the first box that I opened had a bunch of nails in it and 4 or 5 pieces of window cane, like the corals, the square with the lead came on it, and I was like, this is cool. So initially we were thinking about doing a full architectural study, but the XRF study turned into something much larger than we originally thought it was going to be. So it sort of got refined down from an overall vernacular architecture study to focusing just on the glass. And now I love glass a lot.
I totally understand. That's how I picked my thesis topic based on which had the least amount of objects on the site. Okay, so we have you checked 18th century glass to see if the trends you see with regard to 17th century glass hold? In other words, do you see high strontium levels in most 18th century glass?
That's a super good question. So going into the 18th and 19th century, So because there is a wider variety of locations that are using kelp as a flux, you get a little bit more variety. There definitely, most people are making window glass with that kelp flux. So most, if not all, window glass has that high strontium. It isn't as focused, so it does have that similar high strontium range, and you do see that high strontium range sort of skyrocket a little bit later. But that only works for window glass. Because if you look into like the lead crystal glass, that those types of tablewares for glass have things that are more, I'm trying to remember, they use a different type of potash and they have a much lower strontium rate. So it's only really good for window glass. And then in 1835-ish, the number gets cut off sort of completely because the production changes totally based on the Chance brothers, who were working on a different production style in France. Sorry, that was a super roundabout answer, but yes.
I think that answers it. We have another question. Is it possible to date glass using, I'm gonna mess this up, thermoluminescence dosimetry?
Yeah. So are you talking about the thermoluminescence that's used to date silica? So at least that type of luminescence that I've worked with has to do with the last time that the silica was ultra heated. I've never looked into it, but I've seen it work with other types of materials, so I don't see why not. I think that type of testing, you do have to destroy the sample, though. I'm pretty sure, I might be wrong, but I'm pretty sure you have to destroy the sample to complete that type of test. So what you can totally, but I think XRF might just be better for people who are into conserving their materials. There might be just some issue with that type of collections, if that makes sense.
Okay, we have our last question. Hi, Grace. Have you heard of any researchers using XRF analysis to identify differences between late 18th century to 19th century American glass manufacturers?
So when you start looking into the later centuries, like thinking about the turn of the century after the American Revolution, a lot of people start to use, there's thickness methods to date glass based on how thick it is. And a lot of people, that's super regionally focused, and it depends on the type of deposit you're looking at. And I know a bunch of people have been doing that, and I see a lot of that when reviewing reports. A lot of people use those types of methods. I don't think, I've seen people date stained glass from the 19th century, but that's based on the different types of colorants that they're using. I haven't thought about the transition, though. I'll look into it. I hope so.
Great, cool. We just had one more question come on in.
Sure.
So they're interested to know if this was your first project using pXRF in this kind of analysis.
Yeah. So this was my first. I had never used XRF before. When I was talking to Krista about different architectural studies, Dave Landon, who is also on my committee, also wonderful. He sent me the article by David Dungworth, who was one of the first people to sort of build this type of method. And I brought it to Dennis, our conservator at UMass, also wonderful. And he was really cool with showing me the ropes and bringing me literally step by step through the whole thing. So it is my first time using XRF, but I'm trying to convince my boss to have us get a pXRF so I can do more. Excellent.
Well, thank you everyone for joining us for this week's Diggin' In episode. Join us in 2 more weeks when we have Dania Jordan, also from the National Park Service, who will be speaking, one of Grace's colleagues. Thank you, Ms. Bello, for speaking with us today.
Thank you so much for having me, and thank you everyone for coming.